okay? So let's suppose I'm going to draw a similar kind of graph out, but over here. In fact, no, let me make some space. Yeah, let me just rub this off. Okay, because my idea is, what I want to do is find the gradient of this tangent. Find the gradient of this tangent. Now just remind me, how do we calculate gradient at the moment? So how do we know how to calculate gradient at the moment?
There are a couple of ways.
Okay, so give me any of them.
y2 minus y1 over x2 minus x1.
Okay. What's another way?
We can like calculate it from the graph, like
Yep.
rise over run.
Okay, rise over run, so you could say change in y divided by change in x. Yeah, you happy with that? Now have a look at this. In fact, have a look at this formula, right? How many points do I need in order to calculate the gradient?
4.
How many?
The first formula?
So that's 1 point, right? x2, y2.
Okay.
And that's another point, x1, y1. So how many points do I need in order to calculate the gradient? I need 2 points. So in order to calculate the gradient at the moment, I need 2 points. But have a look. My definition of a tangent, that's the gradient that I want to calculate. How many points do I need? There's only 1, right? So can I work out the gradient at the moment? No. So what am I going to do? So okay, let me draw out a different diagram then. Let me draw it out over here. So make it a bit neater because there's quite a lot going on here. Let's suppose I just have some general curve. Okay, so let's suppose I have a curve that looks something like this. And let's just say this is just any general curve, y equals f of x. Could be y equals x squared, y equals x cubed, y equals sine of x. Doesn't matter. Okay, it's just y equals some function of x. But we can assume that the function is non-linear. Okay? And let's suppose that I want to calculate the rate of change at this point here. So I want to work out how quickly my money is changing at this particular point in time. How much money am I earning at this particular point in time? So this is the tangent line that I want to work out. Okay. So let's just talk generally. Let's say that this is x. Okay. And let's say that obviously if that's x, the function is some function of x. So the y value has to be f of x. Happy so far? Okay. So here's my question. How do we find the gradient of this tangent, given it only touches the curve at 1 point? We've got a problem. Are you happy with the problem? My formula for gradient requires 2 points. Okay? It requires literally a change in y and a change in x. It requires 2 points. But my tangent only touched the curve at 1 point. So what could I do? Well, this is my point. How? Differentiation is all to do with finding the gradient. How are we going to find the gradient of this tangent? Okay, so if we draw the tangent further, there might be a point, so this might curve round and come back down here. Good. This is a problem that was faced by well, a lot of mathematicians, right? Because you can see this is important. We want to know how quickly my curve is changing, right? But it's an issue because we've only got 1 point to do it with. So you're right, you could think about this as, well, the curve could come back again, and then you could find out the point over here. Then you'd have 2 points. But why is that not very good? Because this could be, for example, like a y equals x squared graph. Then in which case, we know this curve will never come back again. So it's a good idea, but I'm not quite sure we're there yet.
How about the point that passes through the axis?
Okay, the point which passes through the axis. But the issue is the curve might not pass through that point as well. Like, I want 2 points which I definitely know lie on the curve. Right? Now, this was a problem which was faced by a lot of mathematicians, actually. And in the end, it was solved by 2 mathematicians completely independently of each other. So who has heard of this guy? Sir Isaac Newton. Right, okay. So very, very famous scientist. He kind of was looking at this problem. In fact, he came up with the solution. There is also another guy, which I think is spelt like this. Leibniz. He was also a mathematician working on it exactly the same time in a completely different country. He's German, he's English, okay? And they came up with the same solution at exactly the same time. Now, if that doesn't smell fishy, I don't know what will. But actually, there was a lot of arguments over who actually came up with the solution to this. Like, Leibniz was saying, no, it's my work. And Newton was saying, no, it's definitely me that came up with it. So in the end, we just say, hey, do you know what? You both came up with it, right? But yeah, these are the guys that came up with this. I mean, this differentiation, because it's so important, like it's literally the maths of change, this is a real game changer in mathematics, real game changer, okay? So here's the solution. Here's what they did. They chose a point which is really, really close to it, really close to it. So I'm saying like within 0.1 of it, okay? So they chose a point over here, say. Now, obviously, I've blown this up for the sake of kind of clarity, but imagine this is like really, really close to it, okay? So they said, well, okay, let's just define the distance between these 2 points. Let's call it h. I think they called it h for height, okay? So if this is x, what would this point be? If this is x, then we move a distance h away from it. What would this point here be? Yeah, just be x plus h, wouldn't it? Do you see that? Yeah, x plus h. Well, okay, if this is x plus h, and this is the curve y equals f of x, what would this point up here be?
F of x plus h.
Absolutely right. F of x plus h, okay? So literally all they've done here is they've just chosen a point which is really, really close to it, like really close, right? And then they say, now we've got 2 points we know lie on the curve, okay? And then we can find the gradient of this. So you can find the gradient of this line, okay? Obviously it's not exactly the gradient of the tangent, like it's out a little bit, okay? But it's good enough, it's a good enough approximation. So let's think about this. How would we find the gradient of the blue line? How would we find the gradient of the blue line? Okay, good. So y2 minus y1. So it's change in y. Okay, so we'll write change in y. In fact, I'll do this in blue as well. Good morning, Riley. That's absolutely fine. In fact, I've got some homework here for you. Yeah, you're the fifth. Good. So we've got change in y and change in x. Okay, so the gradient of the blue line, that's what I'm interested in at the moment, the gradient of the blue line. Okay, what would this be equal to? What would this be equal to?
The gradient.
How do I find the gradient of the blue line? So change in y, what is my change in y?
F of x plus h minus f of x.
Absolutely right. It's literally that minus that, that's my change in y, right?
Ooh, I know that rule.
Right, what's my change in x?
X plus h minus x.
Or by definition, that's just h. Yeah, good. Okay, so that's the gradient on my blue line. That's my gradient of blue line. By the way, my red line is a tangent. It touched the curve at 1 point. If it passes through the curve at 2 points, a line which passes through a curve at 2 points, does anybody know what we call that? Okay, a chord would just be the bit in between those 2 points. Okay, but if I continue this line so it continues indefinitely, it's definitely a straight line, does anybody know what we call it? Call it a secant. Call it secant. Okay, so did you know what it was in
My language.
your language? Yeah. Okay, so tangent touches the curve at 1 point, secant touches the curve at 2 points.